Next we're going to talk about different ways to set up your experimental design to make it as robust as possible. To describe different experimental designs, we use symbols. The symbol O refers to the measurement of the dependent variable. If you do multiple measurements of a dependent variable, you refer to it as O1, O2, O3, and so on. For example, when you have a pre-test and a post-test, the pre-test would be O1, the post-test would be O2. X refers to the manipulation or change of an independent variable, so basically your experimental treatment or stimulus. R stands for randomization, so random assignment of respondents or participants, subjects we call them, to the experimental group or the control group. And then time is shown horizontally, so going from left to right is how time passes by in the course of an experiment. Some experimental designs consist of a pre-test and a post-test. The pre-test preceding the experimental treatment, the post-test following the experimental treatment. So a pre-test would be shown as O1, a post-test would be shown as O2. Simple example would be if you ask people their opinions about smoking as the pre-test, then you give them a PSA, for example an anti-smoking campaign, and then you measure how they feel about smoking, so their opinions about smoking again. So you do a second measure of that same variable after the treatment. The different experimental designs are categorized as pre-experimental, true experimental, and quasi-experimental. The true experimental designs have the strongest internal validity, so they're set up in a slightly more complex way, but this complexity brings more robustness and more guarantee that whatever effect you find is truly caused by your independent variable and not by something else, such as an extraneous variable or a confound. Let's start with the pre-experimental designs. Pre-experimental designs, honestly, they offer very little or no control over these extraneous variables. So they don't have a very strong internal validity. Still, they're very commonly used because they're very easy to set up and therefore often used in the industry. There's three main types: the one-shot case study, the one-group pre-test post-test, and then a static group comparison. A one-shot case study looks like this. It's basically one independent variable followed by a single time measure of your dependent variable. That would be, for example, the case if you were to show people an ad and then afterwards you ask people's opinion about that ad. So often this design is done when it's not possible to do a pre-measure. For example, when you can't measure people's opinions about something beforehand because they've never seen it before, they have no awareness of it before. For example, with new developments, let's say, for example, alpha and beta testing, part of beta testing would be you let people use a certain technology and then ask them about the user-friendliness of that technology. You can't ask them about the user-friendliness of that technology if they have not even used it before. However, with a design like this, since it is so simple, it's very prone to confounds. So there could be a lot of things happening over the course of the experiment that make the internal validity very weak. For example, history, maturation, reactivity bias could all affect the results here. A slightly more complex version of this is the one-group pre-test post-test. This is the same as the one-shot case study, except that you have a pre-measure as well. So you have O1 x O2. That means you have that pre-test, then the experimental stimulus or manipulation or independent variable, x, and then your post-test. So at least you have that baseline measure, O1, to use as a benchmark to see if there was any change, any net change between O1 and O2 that could explain the effect. So for example, if you ask people's opinion about something, then you show them an ad, and then you ask people's opinion about that same topic again, you could see if their opinions have changed from moment 1, O1, to moment 2. Third, there is the static group comparison. The static group comparison does not have pre-tests, so there's no O measurements, so no measurement of the dependent variable prior to the manipulation, but what you do have is a control group. So you see the first line is XO1. This means that the experimental group, which receives the treatment or the experimental stimulus symbolized as X, gets asked a question, for example, their attitudes about X, as O1. Now, parallel with that, there is a control group on the second line who do not receive the experimental treatment. So they do not see the ad or the stimulus that is part of the experiment because they are part of the control group, not the experimental group. Now, them, you ask the same question: how do you feel about a certain topic? If there is any difference between O1 and O2, so between the experimental group and the control group, that is an indicator of the effect. However, you still have a design that is very flawed and very prone to confounds. True experimental designs are characterized by randomization. Random assignments, so capital R, to the experimental group versus the control group. So participants are assigned at random to either the experimental group or the control group. True experimental designs are also pretty successful in isolating the effect of the independent variable on the dependent variable while controlling for any potential extraneous variables. In other words, they are pretty strong in internal validity. That doesn't mean they're flawless, but at least with true experimental designs, you have a higher internal validity. The 4 types we're going to discuss is after only with control group, before and after with control group, Solomon 4 group design, and factorial design. The after only with control group looks exactly like that static group comparison we discussed in the pre-experimental designs. The only difference is that there is random assignment from individuals to either the experimental group or the control group. So this random assignment at least helps overcome or prevent the issue of selection bias, for example. So at least you know that the 2 groups, experimental group and control group, are comparable. A more robust design is the before-after with control group. This one has randomization, of course, because it's a true experimental design, consists of a pre-test and a post-test, and has an experimental group and a control group. So in the experimental group, the first line, you see that there is a pre-measure, then they receive the experimental treatment or the independent variable, and then there's a post-measure. In the control group, you have that same setup, except that they do not see the experimental treatment because they're the control group. This offers a lot more robustness. Let me break it down for you. With the before-after with control group, you can really look at what the effect would be. The effect is basically O2 minus O1, so any difference within the experimental group between the second measurement and the first measurement indicates change. If change happened from O1 to O2, so if there's any net difference between O1 and O2, that would be an effect within the experimental group. But also there could be an effect within the control group. So if there's any difference between O3 and O4, that means if there's any change happened between O3 and O4, you have another effect. So if you subtract these from one another and look at the overall effect, the effect being O2 minus O1 minus O4 minus O3, then you could consider the change occurring from O2 to O1 being caused by the independent variable x, but also by various extraneous variables. So there's always a bunch of factors that could act as a confound, disturbing the effect of the independent variable on the dependent variable. The change from O4 to O3 is caused by blank, not the independent variable, because these people in the control group did not get the independent variable. But if there's any difference between O4 and O3, it is only caused by extraneous variables, so those same potential confounds could be assumed to affect the control group as well. So if you subtract these from one another, then you could expect the extraneous variables to cancel each other out, because they're equal in both groups. So as a result, you remain with E, or the effect, being caused solely by the independent variable. So in this case, you have a stronger internal validity because you know that the effect is the change in the dependent variable caused solely by the change in the independent variable. A more elaborate version of this would be the Solomon 4 group design. In the Solomon 4 group design, the first 2 lines are similar to that before and after with control group design we saw on the previous slide. In addition, however, there's 2 more conditions added. The 3rd and the 4th line on this screen shows 1 more experimental group and then 1 more control group. So in total, we have 2 experimental conditions, 2 control conditions. The first experimental condition has a pre-test. Pre-test, treatment, post-test. The first control group has a pre-test, no treatment, and post-tests. And then these 2 additional groups that were added, the first one being a second experimental group, does not have a pre-test. Of course, comes with its independent variable and has a post-test. And then the last group here, which is the second control group, also does not have a pretest. So what do you think is the added value or the benefit of creating two more conditions that lack a pretest? So why would there be two conditions added, one additional experimental group, one additional control group, both of them without a pre-measure? So what threat to internal validity do you think they're trying to solve or they're trying to prevent by making the design so complex? Well, the omission of a pretest in those two additional conditions helps prevent any threat that pertains to a pre-measure. For example, pretest manipulation, interaction bias, testing effect, and so on. So any of those threats that had to do exactly with the fact that there could be a problem with the pretest is being prevented simply by adding two conditions that don't have a pretest. At least this allows you to look into whether there was any testing effect happening or any pretest manipulation interaction bias. Remember, that was called priming. The last category within the true experimental designs are factorial designs. Factorial designs make use of multiple independent variables, so multiple factors or multiple x's that are crossed over into interaction effects. So for example, instead of having just one manipulation, you have two manipulations. An example would be a 2x2 between subjects factorial design. A 2x2 refers that you have one factor measured on two levels, and then a second factor also measured on two levels. For example, factor 1 could be room temperature, cold versus hot. Factor 2 could be test difficulty, easy versus hard. Now let's say you want to know how the combination of room temperature and test difficulty influences students' performance on a test. Then you basically have four experimental conditions. You can create a hard test in 50 degrees, so a hard test in cold rooms, a hard test in 90 degrees, so hard test in hot rooms, an easy test in 50 degrees, and an easy test in 90 degrees. So since both levels, room temperature and test difficulty, so the two separate independent variables, are each measured on two levels, you end up with four potential conditions that participants could be assigned to. Now, most between subject factorial experimental designs are set up to be relatively simple. You don't want to make it overly complex. A 2x2, like the example I just showed, is a good example, but you could also make a 2x3. For example, if you add a third condition, for example right here, let's say a room temperature is no longer measured on two levels, 50 degrees and 90 degrees, but let's say you add a middle temperature room, 70 degrees, then in that case you have three conditions for room temperature and two for test difficulty, making it a 2x3. You could also make it a 3x2, in which case that would mean that you would change test difficulty to become three conditions, hard, medium, and easy, and then keep room temperature at two levels, 50 degrees and 90 degrees. What you could also do is make a 2x2x2 design, which basically means you insert a third factor, so a third independent variable. For example, if the first one is room temperature, hot and cold, the second one is test difficulty, easy and hard, the third one could be noise, quiet versus loud in the room, and then see in which room students perform the best. Now, it's not recommended to make experimental designs more complex than these because it becomes very hard to disentangle the results. With factorial designs, you can look at main effects, which is the effect of one of the factors, so one of the independent variables isolated. In that case, you can just do a two-group comparison. But you could also look at the interaction effect of all factors, so all independent variables combined. In that case, you compare more than two groups, and you have to adjust your analysis accordingly. Now, we're going to be talking about analysis in a separate video, so that is not a concern right now. This is an example of a main effect. A main effect would mean you look at the effect of temperature only, or you look at the effect of test difficulty only on test scores. So test scores are on the vertical axis, so the y-axis, and then you have cold rooms and hot rooms. The interrupted line is an easy test, the uninterrupted line is a difficult test. So what is the main effect of temperature in this graph? So the main effect shows that in a hot room, students consistently perform better, so have higher test scores, than in a cold room. Now, what is the main effect of test difficulty? This graph shows that regardless of temperature, an easy test results in higher test scores than a difficult test. You could also look at the interaction effect, which means you consider both independent variables at the same time. So again, test scores are on the vertical axis, and you see that when a test is difficult, students do better when the room is cold than when the room is hot. Now, when the test is easy, students do better when the room is hot than when the room is cold. You could also reverse this effect. You could say that in a cold room, if you're taking a test in a cold room, you're actually doing better with a difficult test than with an easy test. If you're in a hot room, you do better with an easy test than with a difficult test. An interaction effect doesn't always have to cross like a perfect cross. Sometimes the graph looks like this. And in this case, the interaction effect shows that when a test is difficult, it doesn't matter whether you are in a cold room or in a hot room, your test scores are going to be the same across the board. However, when you get an easy test, you're actually better off in a hot room than in a cold room, because you see the test scores are higher when the room is hot for an easy test than when the room is cold. Looking at the effect in a reversed way, you could see that in a cold room, it doesn't matter whether you get an easy test or a difficult test because both end up with the same test scores. However, if you're in a hot room, you're better off with an easy test than with a difficult test. So becoming more comfortable at interpreting graphs like this is a very important part of marketing research. The last group are quasi-experimental designs. Quasi-experimental designs are longitudinal in nature, and there's no random assignments of subjects, respondents, or participants to either the experimental condition or the control condition. However, since they are longitudinal in nature, you do have some control over the internal validity because you can follow up the effects over time. There's two main types, interrupted time series and multiple time series. Interrupted time series mean that you have multiple measurements of a dependent variable, followed by, at a certain point, an independent variable, and then again multiple measurements of your dependent variable. This is often used in tracking studies, where, for example, a fast-moving consumer good company tracks their sales over time. So every month they keep track of their sales, and then at some point there's a promotional campaign for a product, and then they keep measuring their sales afterwards. So the good thing about this type of design is that it shows you any trends that can happen over a long time. Let's say, for example, there's already a difference in sales between 02 and 04. Let's say sales are already on the rise. Then inserting a promotional campaign after 04, and then noticing that sales continue to go up after that, that continued increase in sales could be attributed to, of course, the promotional campaign, but it could also be that there already was an increase in sales to begin with. So if sales data shows that there's already an upward trend, then inserting a promotional campaign can magnify the effect that is already happening, but at least longitudinal data gives you an insight into whether a trend was already occurring or not. Multiple time series are the same thing, but in addition you add a control group. The addition of a control group that does not have the experimental treatment gives you much more insight into whether any effect is truly caused by your independent variable rather than by a trend that was already happening baseline. For example, if you see an increase in sales between 01 and 08, but you also see that increase in sales between 01 and 08 in the control group, if you see that same increase in sales, then you know that there is an upward trend in sales already, regardless of the manipulation. Now, of course, if you notice that in the experimental group the upward trend is stronger than in the control group, then you know that the enhanced effect, the enhanced positive boost in sales, can be attributed to the experimental condition or treatment.